doing, actually I've been doing this kind of a topic for boundary problem for a bit over 10 years now. So in the talk, I mentioned a little bit of the history, the background, and I'll mention why this is called Fisher KPP. So the traditional equation is with local diffusion. I'll just explain what I mean by local diffusion. Well, that's the diffusion, the usual diffusion we know about. And also I'll talk about this equation with the local diffusion and free boundary. So that's what I started around 10 years ago. And recently there are lots of work on problem with the non-local diffusion. Of course, it started with equations like the traditional Fisher KPP equation. You just replace local diffusion by non-local diffusion. And what I've been doing recently with Wenjie is here, and many other people are continuing on our free boundary version of this Fisher KPP equation, but also replace local diffusion with a non-local diffusion. So we start with the one space dimension, and also mention what we did for high dimension, but with a reduced symmetry. And the ultimate goal would be to consider high dimension without a reduced symmetry, but that's the next step. Okay, now, so let me mention this traditional classical Fisher KPP equation. So, yeah, interestingly, and this Fisher and KPP, of course, KPP stand for these three Russian mathematicians. Perhaps I should say Soviet mathematicians. So they had a paper, well, two papers. So Fisher one, KPP another one, appeared in the same year, 1937. They both independently, in both papers, they tried to use these parabolic equation. We call it semi-linear because the differential equation operators are in a linear relation, and this FU is in general a nonlinear function. So this kind of equations we usually say is semi-linear. So initial value problem, and the space variable here is in R, so one-dimensional model. And they were interested in modeling the spreading of a species in space. And then these are the first papers to try to model these problem, kind of a biological problem, using a parabolic equation. And here they use U to represent the population density. So T is time, X is a space location. And of course, U0 would be the initial population. Because they are interested in spreading, they assume initially the population is localized. In mathematical terms, it means it has compact support. So of course, this is non-negative because it's a population density, and compact support really means so U0x is positive only for x in a bounded set in R. And they want to know, well, what happens when t is greater than 0? In particular, when t goes to infinity, what happens to this population? And of course, this depends on the choice of your function here. This is in general a nonlinear function, and C1 F0 equals 0. And in biological terms, these represent the growth function. And sometimes people call these reaction diffusion equations because this has been used widely to represent a chemical substance, use the density, and then in that context, so this is the diffusion, and this is the reaction. So now in biology, this is called a growth term, and this is a dispersal term. And this diffusion term, we use this standard diffusion term. It really means the population disperse randomly in space. So like a Brownian motion. Now for FU, actually in both papers, they used these. So if you change FU, the behavior of the solution can be very different. But this is a very commonly used nonlinear function. It's a quadratic function, and Fisher used exactly this form. There's a reasoning to say why this is natural. And Fisher, well, KPP, they used a more general kind of FU, but it has basically the same property. And their finding, the most striking fact they proved is the following. So that's why this model becomes useful for describing spreading phenomena. So they can prove the existence of a constant C star positive, so that the population density inside, well, in dimension one, really this is an interval. That's the right hand, that's the right end. The left end would be this with a minus sign. So inside of this enlarging interval with t, and the population density for large time is roughly 1. Outside of that interval, population density is roughly 0. And of course, for rigorous statement, you need to introduce an arbitrarily small epsilon. But this really tells us that, so these phenomena interpreted in biological terms, it means that the population spreads into new space with the speed, this is C star, you see? So in an interval whose right end is roughly C star times t, and so inside the population is about 1, outside is about 0. So you see the population spread at this speed C star. And how to find C star? Actually, they didn't prove, well, they didn't prove this exactly in those classical papers. This result was proved 40 years later by Aronson and Weinberg, mathematicians in the University of Minnesota. But they, Fisher KPP, both determined this C star and kind of imagined this would be the property of the solution, but they didn't prove in that form. So how to find this C star? Well, in both papers, they try to find a self-similar solution for this original PDE. If you look for a self-similar solution of this form, that PDE reduced to an ODE. And then you add appropriate boundary conditions at minus infinity and positive infinity for these self-similar solutions. Well, you can solve it for very general F. So for this particular F, Fu equals this, the quadratic function, the Fisher nonlinearity, they can determine this C star through looking for these kind of solutions. C star is just 2 square root of D. So D is this diffusion coefficient here. As they proved that for C greater than or equal to C star, you can have this kind of a self-similar solution. And for C less than C star, you don't have such a solution. And this kind of solution now, of course, there's a name called the traveling wave solutions, because the shape of this function, the shape of this solution is determined by the profile function V. It's a one variable function. And when t increases, you can see the profile does the shift in one direction with the speed c. And this C star is called the minimal wave speed. You have a continuum of traveling waves with the speed greater than or equal to the C star. And this is the minimal wave speed, and they predict this is the spreading speed. Actually, KPP, they are mathematicians, first-rate mathematicians, and they even proved that if you choose your U0 as a Heaviside function like this, so 0 here and 1 there, and connected somehow in the middle. And they proved that if you choose such an initial function, the solution would convert to the traveling wave solution with the minimal speed c star in a certain sense. Now, this model, now we see is very powerful, useful. It tells us the spreading speed, but of course, it's not perfect. And so in this spreading problem, very often people want to know where's the spreading front. So now, for example, we talk about COVID. We, of course, care very much about where's the spreading front, how far is it to Armadale. But unfortunately, this classical model doesn't tell us where is the spreading front. But of course, that doesn't prevent it from being used widely for describing the spreading phenomenon. So what people do, well, you nominate a small number delta, and you look at this set. So, well, in mathematics, we tend to think, because U is the population density, and then the population range at time t would be the set of X where the population density is positive, right? So you look at this set, that's the population range, or the infected region if the population is a virus. But the mathematics tells us, well, once t is greater than 0, though initially the population is localized. Once t is greater than 0, well, this set actually is the entire R. So sometimes people talk about spreading at an infinite speed. So initially, U0 is compactly supported, but not for any UT. So when t is positive. But to make this, to interpret this population range using the classical model, people usually nominate a small constant and consider this set instead. So if the population density is greater than delta, then we say, well, this population can be observed. So look at this omega delta t at time t. Well, this time, as long as delta is positive, no matter how small, this set is finite for any t positive. It's not like this one. And if we use this interval, well, to represent, well, if we use, we let this to be the smallest interval containing this set. Of course, this set may not be an interval, but because it's bounded, we can find such a smallest interval to contain it. And then use the endpoints of this interval to represent the spreading front. Well, then this result implies, so these endpoints go to infinity at roughly speed c star. So in mathematics, that's what it means. Now, of course, in a practical situation, how do you determine delta? Well, that could be a political thing. But anyway, so, about 10 years ago, a bit more than 10 years ago, with my collaborator, Zhigui Lin from China, Yangzhou University, we proposed a modification of the classical Fisher KPP model. We still use this semi-linear parabolic equation and initial condition. However, we assume in the model, so modify the model. So this equation is satisfied in the population range. So we say the population range is finite for any positive t. But then the population range is changing. So we have to add one more condition to make the problem well posed. So we assume at the boundary, the population density is 0. And on the outside, of course, there's no population. So that's the population range. And then we have to introduce another equation to make this problem well posed. So this extra condition is when Ksay is the left end or Ksay is the right end, we assume we have this condition. And this is borrowed from the well-known Stefan condition and used for determining the interface change of between water and ice, completely different thing. That was derived from the laws of physics. But we just borrowed it here and in an ecological situation, and there are no laws to use, to check. And we just, so in this paper, this is after, this is after that one. In a later paper, by the way, so this Gary Bontin and Chris Krakowski, actually, they were our former colleagues. So, so they are no longer in Armadale now. So we looked at these, and we could deduce these with an ecological assumption. That is an assumption, not a law. So if we assume that K units of a species is lost per unit volume at the front, at the boundary of the population range, then we can deduce these, and mu is just D over K. Now, what's the property of this modified model, the free, well, in mathematics, if you don't know the boundary in your equation, the spatial boundary, and so to solve these, apart from U, the unknown, and this G and H are also unknowns. So these kind of problems in mathematics are called free boundary. Actually, it's better called moving boundary, because they are not free. They are determined by this, by this problem. Anyway, it's called a free boundary. So traditionally. Now, the long-term behavior for this modified model is described by this. Firstly, we proved it's a well-posed. We have a unique solution defined for all time. And then the next thing would be, we want to know when t goes to infinity, what's the long-term behavior of the solution. Well, we have these, so spreading vanishing dichotomy. So either the population range, the interval converts to the entire R, and the population density converts to 1. So that's the case, spreading is successful. But we also have another scenario, it's called a vanishing. So the population range converts to only a finite interval, and the population density converts to 0 uniformly on this changing interval. So this is called a vanishing. And also when spreading happens, again, we can determine spreading speed, though the speed C0 depends on our parameter mu and is different from the C star arising from the classical model. In a moment, I'll explain their relationship. And also, we can determine when does these two alternatives happen. So if we use mu as the parameter, so the mu appears here, is this guy. If we use mu as a parameter, actually there's a threshold value, mu star, so that this successful spreading happens if and only if mu is greater than mu star. Now, how to determine the spreading speed? Well, similarly, we look for a self-similar solution, and this time the modified problem leads us to this problem. Again, ODE, however, the classical problem leads to an ODE on the entire real line. And this time we have an ODE on the half line. And together with the boundary conditions, and here, because we have a free boundary condition, so we have this extra equation. And this is determined by that. We can show for any mu, we have a unique C0, so that when C equals C0, this system has a unique Q. And furthermore, we know this C0 actually is less than C star from the classical model. And when mu goes to infinity, these speed increase to C star. So there's a relation. When mu goes to infinity, so C0 converts to C star. Actually, this relationship is stronger than that. We can show actually the classical problem 1, the Fisher KPP model, is the limiting problem of the free boundary model 2. So if we let mu go to infinity, so the solution and the population range, they have a limit. So the population range goes to R for any finite t, actually for any bounded set of t uniformly. And this solution converts to capital U, the solution for 1, provided you choose the same initial function. So really, so these 2 is more general, and 1 is the limiting case of 2. When you get the parameter mu go to infinity, so mu, the ecological meaning is that, or you let k goes to 0. You would recover from these, recover the traditional Fisher KPP model. And this problem, yeah, I mentioned this Aronson-Weinberg. So the result for these free boundary model 2 are used here come from the first paper with Zhigui Lin and also later papers with Zhongming Guo. They both visited UNE many times, and also with Bendong Lo. So Zhongming Guo is from Henan Normal University, and Bendong Lo is from Shanghai Normal University. So they all visited here a few times. And Guo visited here many times. He first came here as a postdoc for Norman Dancer. And when I was also a postdoc in 1991, I think. Now these problems, equations 1 and 2, so 2 is with free boundary, both they were going to extend to high space dimensions and also for systems equations and various heterogeneous environmental situations where the equations become more involved. So the parameters change with the time and space. But yeah, these result basically, so the result I explained, so things like these for the free boundary problem and things like that for these traditional problem without a free boundary. So these are robust result. So you can extend them to more general situations, but the essence of these phenomena retains. But here I want to stress that in all these extensions mentioned here, so the dispersal is described by local diffusion, random diffusion. And these, in many situations, especially in ecological situations, are not ideal. Very often, non-local diffusion would capture the dispersal more fully. So now, so for that reason, these non-local diffusion problems has gained lots of popularity. So in the last 10 to 20 years, there are lots of new research and powerful people moving into this area. So now let me try to explain what this non-local diffusion really means. So there are many possible ways to introduce non-local diffusion. So here today, I'll just mention one rather popular non-local diffusion operator. So non-local diffusion really means, so when you think about these species dispersal, and an individual at location X in space can jump to any other location Y with the probability given by a given function. Of course, it can be more general. It doesn't have to be X minus Y, but this is a very popularly used, a natural one. It could just be a two-variable function. But in this talk, I'll stick to this simple situation. And with this assumption, then instead of this random diffusion operator, you should have this one. So it's a convolution thing. Now this is y, this is y, dy, and this is x. Yeah. And then the classical Fisher KPP model would be changed to this form. So just to replace this term by this non-local diffusion. Now, what does that mean? So we use it all the time, but usually to deduce this term, use a discretization process, discretize time into steps and space into small blocks or intervals in one space dimension. So this local diffusion really means an individual at any location x is a time interval, moves to the neighboring neighboring interval to the left or to the right with the probability half. You cannot stay without moving. You have to move either to the right or to the left, but the next interval. So the difference really is, so with this non-local diffusion, you can move to any other interval when you discretize space. So that's the difference. Then you introduce the probability kernel or convolution kernel. So you have these. Now, well, sometimes people just make some simple assumptions to focus your research. So one widely used set of assumptions are just J continuous, non-negative, even, and normalized. And then, well, if you change the local diffusion to non-local diffusion in the problem, then what kind of fundamental change you can have? Well, there is a change. And one important thing is about the spreading speed. And to say this change, well, you have to single out the conditions in terms of these kernel functions. So one important condition is the so-called thin-tailed kernel. So if this integral is a finite for some lambda, then we say this J is a thin-tailed kernel. Otherwise, we say it's a fat-tailed. So what's the difference between thin-tailed and fat-tailed? Well, for thin-tailed kernel, for this new problem 3, non-local version of the traditional Fisher KPP equation, its behavior is similar to the local diffusion one. So you also have a finite speed, and you spreading is determined by some kind of traveling wave solution. But for fat-tailed kernel, there's a new phenomenon called accelerated spreading. So there's a result of a Weinberger, quite an old one, 1982. From that paper, and you can deduce that now if we consider 3, that's the non-local version of a Fisher KPP, and then you have a similar, roughly similar kind of behavior. When t goes to infinity, the population density converts to 1, locally uniform in space. However, if you check the spreading speed, you find a difference. So you have to do the similar thing, because with these 3, again, if you replace delta by 0, is omega 0 t is r all the time. But if you choose delta positive, any delta between 0 and 1, you would get this. So the speed is finite if J is a thin-tailed. It's infinity if J is a fat-tailed. And the C star is again obtained by looking for self-similar solutions called the traveling wave solutions. So that's the big difference. And this limit is infinity is usually called the spreading is accelerating. So the ratio gets bigger and bigger. And how fast can these go to infinity? Now, this recent work of Garnier, he checked some typical kernel functions. So if the kernel function for large x behaves like that, sigma less than minus half, and that's a fat-tailed kernel, and then the speed, so this function would behave, so these two functions, so minus g and h, positive h delta, would behave like this exponential function, yeah, much faster than t. And if it's like that, still, if beta is greater than 1, this is still fat-tailed. Then it's like this, beta greater than 1. And there are still lots of current work trying to getting a final kind of estimate for this accelerated spreading. And also another kind of non-local diffusion operator is the so-called fractional Laplacian. And here is in dimension n. And its kernel now is given by this function, power function, but it's a singular and it's not integrable. So it's very different from these ones. But anyway, for this kind of a non-local diffusion operator and for the same kind of a Fisher nonlinearity, FU, and Cabré and Roch-Jeffrey, they proved, again, this spreading is like exponential. So that's their result. And this sigma star comes from the dimension and the s in the fractional power. So it's between 0 and 1. Okay, that's basically what people have done for this classical Fisher KPP equation. So you replace the local diffusion operator by a non-local one, and you have accelerated spreading. Now, how about this problem with the free boundary? So, well, we look at two. So we replace this by the non-local diffusion operator. And again, the population range is a finite interval. And then, of course, we follow the same kind of ecological assumption, then this equation is changed because of the diffusion process is different. Now, so if we make this change of a diffusion operator, so the free boundary condition is also changed accordingly by following the same kind of ecological assumption. So that's the new problem. And that, so here, so initial function continues positive inside, and for the kernel function, we assume this basic kind of assumption. So, so it's integral is 1. At 0 positive is continuous, non-negative, and even, and bounded. And again, we choose this F, the Fisher nonlinearity. And that's just an observation. So this term can also be written that way. So in this particular situation. And I think I'll just skip this. This is just an explanation how you can use the same kind of ecological assumption to derive this condition. So this problem 4 was first considered in this paper. And Yihong Zhao was here for 1.5 years as a visiting PhD student. And this was her PhD supervisor in Lanzhou University. And Fang Li is from Guangzhou, Zhongshan University. She visited here a few times. And there's another paper published in the same year, but it's independent. We don't know each other's work, though I know Fernando And he visited here in 2015 for a month with a paper. But we didn't know, we were both looking at this same kind of problem, but they looked at the case, f is identically 0. So, the free boundary conditions are the same by coincidence, but it's also natural because you look at the same kind of ecological assumption, you would derive that. But in their paper, because f is identically 0, then the long-term behaviors are very, very different from what we got here. So we have this f, the Fisher nonlinearity. But anyway, so we showed that the problem is well posed, and the long-term behavior is similar, spread and vanishing dichotomy. So this behavior is just the same as for the local diffusion case. And when we check when does this happen, the two alternatives happen, we can decide these precisely. Well, here we already notice some differences from the local diffusion free boundary model. And then when we look at the spreading speed, again, so it's here we found the fundamental difference. So again, so we can have accelerated spreading. And for the free boundary model, the threshold condition of the kernel function is this one. So we call it J1. So this is integrable times x. We call that for the thin tail condition, it's multiply e to the lambda x for some lambda positive. So that's different. And we can show that if J1 hold, we have a finite spreading or linear spreading. So this G and H grew linearly in time. But if J1 does not hold, we can show it's accelerated spreading. So this is joint work with Fangli, the same Fangli, and Maolin Zhou. So Maolin was a postdoc here. He left last year to China. So now we also figured out the threshold condition on the kernel function for the free boundary problem. And then of course I should also mention how to get the C0. Well, to get C0, you look for a self-similar solution, and in the non-local diffusion setting, that's the problem. And we can show, so this problem has a solution when J1 holds, unique solution, and it has no solution if J1 does not hold. So that's how to determine the C0. So J1 hold, we can determine C0, we have a linear spreading. J1 does not hold, we don't have a C0. Of course, you shouldn't, because the spreading speed is infinity, it's accelerated spreading. And then it's interesting and difficult to check. So how these accelerate spreading, in that case, how does this go to infinity, at what rate? And also, we want to know some sharper estimate than this one for the behavior of HT and GT, even in that case. So that is a recent work with Wenjie. Fortunately, that one is terribly long, 82 pages. So we...
Say terribly long. Long.
Terribly long. So we checked, so what happens if the kernel function behaves like x to the minus alpha for large x. And we want to get some sharper estimate. But for this kind of function, we can check, so these two conditions, the basic assumption J means alpha has to be greater than 1. And the condition J1 means alpha greater than 2. So J1 is just here. So it's very easy to say that. Now, what can we say about this behavior of H and G for these special class of kernels? Well, if alpha is greater than 3, so we are in that range. So this difference is bounded. So previously we know the quotient goes to C0. So now this is a sharper. So the difference is bounded. But if alpha is between 2 and 3, this difference is no longer bounded. So if alpha equals 3, the difference is log t order. And in this range, between 3 and 2, it's this order. So this is sharper than just seen. So this quotient has limit to C0. And now, in the remaining case, that's when alpha is less than or equal to 2, but greater than 1. Yeah, that's this case. If alpha is 2, so this is accelerated spreading. So this goes to infinity quicker than t, but it's like this. And if this is between 2 and 1, it's like that, still faster than t. Yeah? So accelerated spreading. Now if we compare, so 3 is nonlocal diffusion without a free boundary. 4 is nonlocal diffusion with a free boundary. In both, accelerated spreading can happen, but in 3, the nonlocal classical Fisher KPP equation, and accelerated spreading happens if and only if J thing does not hold. So this happens if and only if J1 does not hold. So J1 and J thing, actually they are comparable. So this implies that, but not the other way around. So therefore, accelerated spreading happens less often for the problem with the free boundary than the one without a free boundary. But of course, we can also compare with the random diffusion model, either 1 without a free boundary or 2 with a free boundary. If you have a random diffusion, accelerated spreading never happens. So that's the big difference. Now, more recently, again, around people with Wen-Jie, we look at the case in high dimension with the radial symmetry. And then model 4 would be in that form. So instead of an interval, we now have a ball with the radius ht. Ht is x equals ht is the free boundary. And the boundary of this population range, which is a ball, is 0, and we have accordingly the free boundary equation is like that. And again, we take f, the Fisher nonlinearity. We don't have to, we can allow for more general f behaving similarly. And for the kernel function, that's the basic assumption. And that's the radial high dimension version of the old J. Now for this problem, and if we introduce this new J tilde obtained from J in this way, and we can rewrite 6 into this form, kind of comparable to the one-dimensional situation. But then here you can see differences. But it's related to the one-dimensional situation. So we can show this problem is well posed, and we have spreading vanishing dichotomy. It's just similar to the one-dimension case, to the local diffusion situation. And we can determine exactly when these two happens, and we have these complete classification of cases. And then I just want to stress, well, what's the spreading speed? And this is complicated. So we have to introduce another function, J star, obtained from the radial kernel function. And we have to use this to determine the spreading speed. I think I can manage to finish in time. So the spreading speed, we can show depends on whether J star. So that J star defined in this way. Satisfy this condition J1. J1 is to say x times J star is integrable from 0 to infinity. So if J star satisfies J1, we have a finite speed. If not, infinite speed. That is to say accelerated spread. And we also looked at a sharper estimate than this one. And the first case we looked is for the case where we have a finite speed. And a typical situation is when J has compact support, then J1 is definitely satisfied. And we checked, we found this difference is unbounded. It's of the order log t, ln t for large t. And that's different from the one-dimension case. In the one-dimension, I didn't mention it, but in the one-dimension case, I think it's mentioned here. In the one-dimension case, if J has a compact support, this is bounded. And so though I didn't mention it, but it's contained in that paper. So that's the difference from a one dimension to high dimension in the finite speed case. And for the accelerated spreading case, J1 does not, we again looked at a function behaving like, so this J is in high dimension and R means X norm. So JR behaves like R to some power minus beta. And then we found, so J1 does not hold is equivalent in that situation to beta in that range. So J1 does not satisfy, J star does not satisfy J1 is equivalent to, in that case, is equivalent to beta in that range. Well, in that range, we can check. So the rate of convergence to infinity is like that when beta is in this range, and when beta equals n plus 1 is t log t. Now, okay, yeah, now we mentioned here some problem we cannot answer now. So if J behaves like that, but beta is greater than this. So it's not in this range, but beta is greater than that. And then J1 is satisfied. And then we have a finite speed. And then what happens to these? So our method cannot cover that case. So we don't know. And the other conjectures we have would be, so you see in all these results, we just have these kind of relationships. So this means this over that is bounded from both above and below by positive constant. Now, can you say you have a limit? We suspect the limit exists, but so our techniques are not enough to get this. And similarly for these two cases, we suspect the quotient has a limit, but we don't know what are the limits because our techniques are not enough. And some other extensions is to systems in dimension 1. We had some papers. I didn't mention everything. I think we have some recent ones. I have another recent paper with the team submitted, but not listed here yet. These are mostly joint work with visitors. For example, Meng Zhao was here for 1.5 years. He left last year as a visiting PhD student, also his former student from Lanzhou University. And that's Wen Jie here. Mention Wang, he visited me many times. We had many joint papers. Yang Zhang visited me as a visiting scholar for 1 year. So left January last year, I think. I think that's all. Thank you.
So a comment, I'm not surprised about the Fisher KPP function, because this is what we have in the logistic model.
Yeah, it's also called the logistic model.
Exponential growth, if you have a low density, and if the density comes to the carrying capacity, it slows down to zero. So that's the simplest. You can have this behavior with a linear term, but it's the simplest function you can have to model this behavior. It's nice to see that first year.
This is called the logistic equation. Initially, people in ecology just used the ODE. And then I think, so this Fisher KPP paper appeared in 1937, partly perhaps because of the Second World War. They didn't catch the deserved attention in the math community until in the early 1950s, after the Second World War. There was a paper by Scanlon, a British statistician, and he just promoted the use of random diffusion to describe dispersal of species. Of course, at the beginning, ecologists were very against such kind of use of, because animals don't behave like molecules in the air, Brownian motion. And but eventually, people accept that, because using these, and you get lots of phenomenon. It's very reasonable. The spreading speed is very reasonable. And there were, I think many years ago, I'll give a talk with some details. And people check the spreading speed C star. You can calculate using 2 square root d, for example. Actually, if you, for a general f, instead of u times 1 minus u, and you should have 2 square root d is the diffusion rate, and then times derivative of f at 0. And people check these against observed data for many species. For many examples, they agree pretty well, actually. So eventually that gained acceptance, but still, I think in ecological, biological problems, math is used and also abused a lot, because you don't have the principles. So you can just come up with a reasonable function, reasonable model to use it. And it's not like mathematical physics. Very often you have your model is based on proved or experimentally confirmed laws. So in ecology, biology, no. And now you can say you can use Fu equals U times 1 minus U. There are also many other choices. And for similar choices, like the ones in KPP, its behavior is similar. But you can also choose very different one. Actually, there are 3 kinds of Fu. So the one we use, the Fisher KPP one, also has a name logistic or monostable. And there's another one called a bar-stable. It's also used in other places, known as Kohn-Hilliard kind of a model, or Alan Kohn. And there's another kind of combustion model. So these are 3 important kinds. And for many of the results I talked today, there are also versions for those kind of nonlinear functions. But the Fisher KPP one is one used most widely in biological and ecological settings.
What about epidemiology? It's the same sort of sociological phenomenon?
Yeah, so now here actually several models here are academic models. These are systems of equations. systems of equations. However, it turns out behind the scene that the property of the model looks like these Fisher KPP. That's the reason we can handle several of these.
Generate papers.
Yeah. So behind the scene is similar ideas. You can handle those models. Of course, there might be small difficulties, but because of the phenomenon is similar, and we have a spread and vanishing dichotomy, the long-time behavior, it's all similar. Though, yeah, you do have differences here and there, but these are small differences. So the mechanism behind are similar.
Yihong?
Yes?
Can I ask a question from the
yes.
laptop? So, Yihong, you mentioned early on that the idea of using a parabolic equation like KPP to model this sort of growth or spreading problem was quite original in 1937. You mentioned that Kolmogorov was, yes.
Yeah.
So how broadly are parabolic equations used in this regard? You said that one of the early solutions that both Fisher and KPP considered was a traveling wave solution.
Yeah.
Is the analysis or the tools that you use to analyze parabolic equations like this, for instance, similar or very different from the ones you might use to analyze an equation like the KdV equation, the one that has soliton solutions? Is that a very different sort of analysis? Or?
It's a very different, yes. The solitons, they are from hyperbolic models. And it's also like a traveling wave solution, but really behind the scene, the principles are rather different. On the other hand, so now with parabolic equations or systems are the most widely used models in mathematical biology. So now there are many models. They don't look at traveling wave solutions or spreading. They are just interested in survival or extinction kind of questions. They also use these parabolic models. Part of the reason is because traditionally most population models are ODE models. And then people realize that, well, you consider an ODE model, you don't take into space variation into consideration. That's not realistic. And then the most natural thing to introduce this spatial variation is by considering the species, individuals of the species would disperse in space via random diffusion or now nonlocal diffusion. The nonlocal diffusion is particularly popular recently because you have so many choices of your kernel function. You can just, if you have a particular problem, and you can use data and try to figure out a more suitable kind of a kernel function. Now, this other story is about this long distance dispersal. So now, because when we talk about COVID, we travel, we fly. All these are, of course, long distance dispersal. Of course, using these kind of models to model COVID, I think is unrealistic. There are more realistic models. But more or less, this long distance dispersal happens even with the spreading of mosquitoes. So you import wood from other countries, mosquito came in. All these are by long distance dispersal. And also you think about spreading of plant species. Seed can get carried by car, by whatever, to long distance. All these things now this non-local diffusion, I think is just is very, very early days. There are so many basic questions unanswered. However, that is a direction that might find more and more applications. So because there are so many kind of dispersal phenomena involving a long distance dispersal factor. So this non-local diffusion model, by choosing proper kernels, you can capture this kind of a factor in the modeling process. Yeah.
Are there applications in the military, in the war?
Well, I heard people talking about, actually, Barsdiki talked about using these kind of models to analyze criminal kind of activities. Yeah. And so I'm sure the military can use it, but I don't know. So we mathematicians, especially like me, mainly a pure mathematician, just look at oversimplified models, try to dig out some general properties. So these are usually far from being applicable directly. However, that can help more applied people to find more useful models. You know, you have a very basic one, then they have to modify it to suit their special need. So we just try to provide some kind of a deeper kind of a result, but for oversimplified models.
So the mode of, say, when you write open questions in your previous slide,
Yeah.
Are they sort of just curiosity? So like,
yeah, I think these are
curiosities.
Curiosity. Is it, I think only we pure mathematicians would care.
Okay, so
Yeah.
like, it's not like
No. You see, so in this data in ecology, usually to find the diffusion rate D, an animal is given, you don't get 1D, you get a range of D, like from 0.1 to 5, such a big range. So you don't, and for the spreading speed C star or our C0, and we found the exact value, but you see there are so many uncertainties in your model. The parameters, you cannot determine an exact parameter for your problem. You only have a range. So what you can do is, well, I predict these phenomena. There's a spreading speed. Exactly what? Then you get a range. If the range is not like 100 times or 20 times different from the observation range, you will think, that's a reasonably good model.
So you're trying to show universal qualitative behavior.
Yeah, but for mathematicians, you want to know, was this number, that depend on dimension n, yeah? And I guess we depend on the dimension n. But in reality, either you care about the dimension 2 or dimension 3. Yeah, but we are interested in all dimensions. Sometimes you get, dimension 8 is critical. Above dimension 8, things are different. You get excited a great deal, but it's just our pure mathematicians.
If you have vanishing, can this also happen in finite time?
No, these kind of models. So if you have a solution, it's defined for all time t. And in our model, in the population range, it's always positive. Yeah, and you get 0 when t goes to infinity. Yeah. Of course, there are other models. They do have a finite time vanishing, but not this kind of. And also there are models you have a finite time blow up, but not with this kind of logistic nonlinearity. Yeah.
Stop it there, I think. So explain Yihong again. And yeah, so the other thing is Martin here is new, this is Martin Sticker, who's a PhD student. Everyone seems to have left, so this is Yihong. Yeah, so that's that. I think.